All right, we're going to start chapter 7, the energy equation. We're going to see that we can apply the Reynolds transport theorem to energy just as we have applied it in the past to mass and momentum. This will allow us to do some interesting problems in fluid dynamics. So looking first at our roadmap and our learning objectives, we can see that this chapter describes how conservation of energy can be applied to a flowing fluid. And as we'll see in these first two introductory sections, that we are really looking at both a closed system and how energy exchange can occur within a closed system, and then we're going to use the Reynolds transport theorem to apply it to both our Lagrangian and Eulerian points of view, closed and open systems. And we can see that in section 7.1 and 7.2, we're going to be both learning the meaning of energy, work, and power. We're going to be looking at different categories of energy and defining what pumps and turbines are. This is really important in using in applications of the energy equation, in that we're able to apply pumps to basically gain energy or to input energy into a system, and then to use turbines to extract energy out. And then finally, we'll just tack on section 7.2 here quickly to explain conservation of energy for a closed system and a control volume. It's a quick section. So let's get going. So energy concepts. Energy is the property of a system that characterizes the amount of work that a system can do on its environment. Notice the sign here of the work, the amount of work that a system can do on its environment. This is going to be very important when we look at the signs of quantities in the energy equation. So a good example, or some good examples of these, are water behind a dam. We basically have potential energy sitting there, and as this water flows through the base of a dam from higher elevations through the dam, we realize that energy conversion into turbine energy from which we can extract energy. And obviously this is the principle of hydroelectric power generation. Another example is wind energy, or wind, the velocity of the wind passing across the blades of a windmill, which turn basically another turbine. A windmill is just a turbine that is responsive to the wind, and as the blades turn, as the wind basically imparts energy to the turbine, the vanes of the turbine, we can extract energy from that. And then finally, another example is gasoline that's put into an engine. And we can burn that chemical energy from the gasoline and basically turn it into mechanical energy, as we do in our vehicles. So we have, we've seen this before, that a unit of energy is a joule, and that a joule is equal to 1 Newton times 1 meter. We'll see that this makes sense here when we look at the definition of work here in a minute, or energy. And we have the situation where we have 1 calorie with a small c, and energy calorie is equal to 4.187 joules. And 1 kilocalorie, or a food calorie, let me just write that down. This is a food calorie. These are the ones that we see on the packaging of our food. It's actually a kilocalorie, a kilo energy calorie. So this is 4,187 joules. And so we could write, if I get back to a black pencil here, we could write, we note that there are 1,000 little calories, little c, in 1 food calorie, where this is a capital C. And we can do a nice little conversion. I'll just do this very quickly. Most of us eat around 2,500 calories a day of food. This is a capital C, just making a little bit of a look like a capital C here. We can multiply that by 4,187 joules per 1 kilocalorie here. And then we can divide that by 1 day. because we eat that in about 1 day, and we can then convert that into seconds by 24 hours divided by 1 day, and we have 3,600 seconds in 1 hour. Whoops. 1 hour. And we can see that the hours are going to cancel, the days are going to cancel, and the calories are going to cancel. And our units here, we're left with 2,500 times 4,187 joules. All over, I'm sorry, that's 86,400 seconds. And if we do this math, this is going to equal 121 joule per second, and of course that equals watts. So we are generating, or we are eating this much energy each day. If we eat 2,500 calories, we're actually eating 125. If we do that in 1 day, that's a rate of energy consumption, and that equals 121 watts. So as you're sitting in class or sitting at home watching this video, you're burning about your energy consumption is about or energy production of your body is about 2 60-watt light bulbs. So energy can come in many forms, as we've seen before. I'm sure you've studied this before. We've got mechanical energy, which is usually kinetic and potential energy. There's thermal energy, chemical energy, electrical energy, and nuclear energy. They're all these different forms, and we know that we can convert from different forms to others. For instance, we could use potential energy to get electrical energy, as we do in hydroelectric power generation and so forth. Actually, that's usually potential energy to kinetic energy to electric energy, but we know that we can convert between different forms. And of course, we can never create energy. We can convert it, and we lose it sometimes due to heat and other processes, friction and things like that. So it's never a perfect process. It's never 100% efficient to convert, but we can do this. So if we look at the definition of work, we've seen this probably before in physics class. The work done on a system is when a force acts on that system over a certain distance. And so we just have a vector quantity here. Actually, these are two vectors, the dot product of these two vectors, which create a scalar. So work is a scalar, but it's basically a vector force dotted into the direction in which that force is acting, and the ds from one point to another, S1 to S2. So that's kind of a definition of one definition of work. And just some examples of that are a spray bottle for fluids, are a spray bottle where you're applying force to this piston or this plunger here, which is basically causing fluid to flow up into the nozzle here of the spray bottle and out. So the action of the piston is doing work on the fluid, pumping it up, giving it potential energy, and spraying it out the nozzle. Another example is the turbine again, where we have wind coming from right to left. It's producing a torque on these blades, which is spinning the turbine, which is housed inside this thing here, and is creating energy, which can be transferred out by electrical wires. The power is just the rate of work done on a system. And so that simply is a definition. We can see that that's the 3 lines there right here mean that it's a definition. It's just the quantity of work or energy that's done in per unit time. And so it's just the limit as the time goes to 0 of the change in work over the change in time. And we write that as W dot. So basically power is work done, the rate of work done, or the rate of energy consumed. And there are different forms of power. This is pretty easy to understand from our definition that we just saw. The work is the force per distance. This is and we see, so this is F times some delta x. We're applying some force over some certain small distance for a certain small time. But of course, delta x over delta t is just the velocity. So the power for rectilinear or linear motion is just force times velocity. And the counterpart for angular motion, which we haven't talked too much about in this class, is just the torque times the angular velocity. So the final concept in 7.1 is to define what a turbine and a pump are. And this is very simple. A turbine is a machine used to extract energy from a flowing fluid. So this is going to be something that's subtracting energy from our system. We can think of that easily in terms of a turbine at the base of a dam. We're using the potential energy of the water flowing out of the dam through the turbine to turn the turbine and create energy, extract electrical energy. The pump, on the other hand, is a machine used to provide energy to a flowing fluid. And so a great example of this is a water pump in your home. That may, for those of you who have lived with well power, or well water that comes from a well, a physical well, you need a pump to pump that water up to your house and to create enough pressure to use in your home. So that's it for section 7.1. I'm going to continue on with 7.2 quickly here. The Joule's theory of energy conservation says that energy of a closed system can only be changed in two ways. And so I'm curious if you know what these two ways are. Can you think of two ways to change the energy of a closed system? The two ways are work, and also the second is heat transfer. So just to explain those two a little bit more in words is work is really going to be interactions of a closed system. Okay, so we need to think about what we're doing in a closed system. The work done is really the energy of a closed system across the boundaries. So it might be something like a piston. You might have a piston. If you have a closed system inside this system here, you might press down on this piston to do work on this. And that might be an example. We're applying some work on the piston and we're changing the energy of the system by maybe raising its temperature or something like that. Heat transfer, on the other hand, might be if we're applying some heat to this system. Maybe we have some warmer temperatures out here, and we've wrapped this thing in maybe a heating element, and we're actually applying heat through the walls or through the boundaries of the closed system. And in this case, we might be considering, if you can think of this as a control volume, we might be considering this little thing right in here, the control volume. So any work that we do on that control volume or any heat transfer that we either put into it or extract from it are going to change the energy of that system. So work and heat transfer are the two ways. Note that the energy is a property of the system, whereas work and heat transfer are interactions that are occurring across the system boundaries. And so figure 7.3 shows this. We have some amount of energy in the system, but we can change the energy of the system by either work or heat transfer. And we can extract energy out of that by either work or heat transfer as well. So what does this remind you of? We've got a closed system here. You can see the boundary here, the dashed boundary around the system. We have a quantity of energy inside this boundary, and we can either put energy into it or extract energy out of it. What does this remind you of? It should be reminding you of the Reynolds transport theorem. It's very similar to what we did for mass and for momentum. And so we are going to look at this now quickly. So the law of thermodynamics says that we have to have a balance of work and energy. And the book talks in more detail about this, but we can consider the increase of energy stored within a system, a closed system, as being the amount of energy that is entered the system by heat transfer and the amount of energy that the system left in the system due to work. Okay, and so if we write that in equation form, we have dE dt is going to equal Q dot, or the rate of energy transfer by heat transfer, and the minus the extraction of work, the rate of work done. And so that's W dot. These can be thought of external energy transfers on our closed system. That's sounding a lot like the external work that was done on the left-hand side of the momentum equation, if you remember. So if we think about a control volume and we want to convert this to an open system, to thinking about it as an open system, say for fluids, how might we proceed? Hopefully you will understand that we should be applying the Reynolds transport theorem to a closed volume, or a control volume. Reynolds transport theorem. This is what we ought to do. So if we look now at the equation for that, this is what we have. We've applied the Reynolds transport theorem, control volume, to an open system. These are basically the external energy components, the heat transfer that is occurring in or out of the control volume, minus the work, the rate of work being done. And that's going to equal the time rate of change of any energy per mass, actually, occurring within the control volume, and any flux of energy across the control surfaces. Very similar to what we've seen before. And so my question quickly are, what are the extensive and intensive properties? One thing that we can do right now is we can remember that that the two things on the left-hand side equal dE dt. So that's a little sloppy. Let me rewrite that because it's important. dE dt. And so what is our extensive property? Pretty easy. And what we're interested in is the energy. That's what we're really working towards understanding in this problem. And this little e that you see come up right here in this, the intensive property, is E, as we've seen before, is just the energy per unit mass. That's what little e is. And we can see that this equation right here is the Reynolds transport theorem for energy. This is the general form, the most general form of conservation of energy for a control volume. And we can see that it is very much like the equation that we had for continuity, and the equations that we had for continuity and momentum. So basically, in the subsequent sections of this chapter 7, we're going to apply this. And just to prompt you, where are we headed? This is actually from section 7.3, but where are we headed? This is where we're headed. We're headed towards using this equation, which looks quite a bit like the continuity equation, actually, and or the Bernoulli equation, in fact. This stuff is slightly different. You can see that we have an alpha term in there and a V bar. Let me point those out. Here we have an alpha and a V bar, and down here, and also we have an HP, which turns out to be the head added by a pump. So we're allowing on this half of the equation to add energy from the pump, and in the second part, that thing's going to equal very similar quantity here. Again, it has an alpha and a V bar. We're going to have to understand what those are. But we also have HT, which is head removed by a turbine, so we're able to extract energy via a turbine here, and also we're going to have head loss um, that we are going to have to calculate as well. So this is where we're headed. It's the summary of the energy equation, and in the next section we'll derive this and begin to use it. Okay, thanks.